Everyone, my name is Jisung. I am a junior in St. Paul American School, Hanoi. I co-lead the H2O Science Club in our school. Today I'm going to talk about Bernoulli's principal experiment, which is a part of our AP-related experiment project in our club. So to give a brief introduction about our club, we were founded in 2019, and as I said, it's a science club in our school. We're in Hanoi, Vietnam, and our club members engaged in science fields, engaged in the science field through research articles, experiments, and activities. So firstly, I'm going to talk about how this principle is aligned with the AP Physics framework, and then go on to talk about what Bernoulli's principle is, and then I'm going to talk about the experiment itself. So the Bernoulli's principle comes out in the very last topic of AP Physics 1, which is 8.4 Fluids and Conservation Laws. In this topic, the continuity equation, energy conservation, work and energy all come together to form the topic. So let's get to know what Bernoulli's principle is. So as you can see, it was invented by Daniel Bernoulli, and he was a Swiss mathematician and physicist, and he was from the Bernoulli family of scientists. And he had a significant impact in the field of fluid dynamics and the kinetic theory of gases. So to explain Bernoulli's principle, we have to know what the continuity equation is. So I'll give you guys a brief explanation of this equation. So as you can see that there's a delta t in both of these equations. The delta t here is the same. So we're basically measuring. So you can see that the fluid has velocities here. So here the fluid has a velocity 1, and here the fluid has velocity 2. We're measuring, so for the same interval of time, we're measuring how much this slice of fluid travels. So the travel distance is represented by delta x1 here. So you know how if we multiply time by speed, we get the distance. So this is what we're doing here. So delta t, this is the time frame that we are measuring, and this is v1. So this is the velocity of the fluid here, and then we multiply those to get delta x1. So this section is delta x1, and here we do the same thing. So delta t, so let's say like 0.5 seconds or something when we're actually measuring it. V2, so this is the velocity of the fluid in this section of the continuous flow. So this is called a flow tube. So it's an imaginary path that the fluid goes, and in here fluid's not created, not destroyed, or incompressible. So we do the same thing here. So delta t times v2 is equal to delta x2. So this represents the small gap around here. So we multiply the time, the same interval time, with the velocity of the fluid here to get this little gap. And you can see that we have A1 and A2 here. So this is essentially the cross section for the fluid. And if you recall the volume formula for cylinders, we can do the cross-section area times this little gap to get the volume of this section of the fluid. So it's basically base times height. So the cross-sectional area is the base, and the delta x here is the height. So the cross-sectional area times delta x is the volume, so we write it here. So basically A1 is the cross-sectional area and V1 times delta t is the height. We do the same thing here. And since fluid is not created or not destroyed in the same interval of time, so let's say 0.5 seconds, so the amount of fluid that passes through in this section for 0.5 seconds and the amount of fluid that passes through this section in 0.5 seconds should be the same, since fluid is not created, not destroyed, and incompressible. So basically they have to have the same fluid flow rate. This is the amount of fluid that passes through a section of the tube in the same interval of time. So here we have the volume equals this thing and this thing. So the volume that passes through the section in the same interval of time is the same. So then we have this continuity equation, but this equation is not important for our lesson today. But the key takeaway here is the volume that passes through this section here and the volume that passes through this section here for the same interval of time, delta t is the same. All right, next, let's talk about what Bernoulli's principle really means and what it relates to. So Bernoulli's principle relates the fluid's pressure, velocity, density, and height of the fluid in a flow tube with the principle of energy and mass conservation. It also uses the network kinetic energy theorem, which I will explain in the further parts of the video. And its most famous practical application is the generation of lift for airplanes. And we will talk about how the principle relates to the generation of lift when we talk more into what the equation is and what it means. So this is the diagram for Bernoulli's principle. Although it's not noted here, we have to know that these sections of the tube is measured over the same interval of time. So in the same interval of time, the tube travels, in this section, the fluid travels this amount of distance, so delta x1, and in this section, it travels delta x, the distance of delta x2. And these velocities are basically these delta x's over the delta t, the interval of time that we're measuring this fluid. Remember, speed is equal to distance over time. And this is the cross sections as we talked about, and this is how this is a diagram of how lift is generated over the airplane wings, and we are going to talk about this when we are talking about the meaning of the equation. All right, so this is the equation of Bernoulli's principle. So the big P right here is pressure. So P1 is the pressure that comes from the left side of the flow tube, from the fluid that is on the left side of the section right here. And P2 is the pressure that comes from the right side. So this is basically all the particles here are pushing onto this section, but since we know that the fluid is going right here, this pressure will be stronger than this pressure. And this little p, which has a rounded top, represents the density of the fluid, and v is for velocity of the fluid. And we talked about how this is the delta x over the delta t. And g is the constant of gravitational acceleration. So this is 9.8 meters per second squared. And lastly, h is the height of the fluid. And this is measured um, this is measured based on the center of mass of the fluid section. So if you can see here, we have the height of the fluid section here, and we have the height of the fluid section here, and the pressures push from here, and the pressures push from here because of all the fluid particles that are contacting the section of the fluid right here. And just a reminder, this section's volume and this section's volume is the same. So in order to understand what this equation really means, it's easy to think of it this way. So if a pipe narrows, the velocity of the fluid should increase to transport the same volume in the same period of time. And as I mentioned, this relates to the fluid flow rate, Q equals A times V. So if the pipe narrows, the area must decrease, which causes the velocity to increase to keep the fluid flow rate the same. So the fluid flow rate is the same for all parts of the flow tube. And the higher speed that's caused from the narrow pipe causes the lower pressure. And this happens because when particles pass through the tube faster, it has less time to contact with the with the exert with the walls of the tube. So basically, we have, let me pull my pen out. So basically, we have this tube here, and then if the particles are going slowly, it has a better chance of bouncing off these walls, right? But which creates more pressure. But if it goes faster, it has less time to really contact with the walls to create the pressure. And the converse also works. So if there is lower pressure, so lower pressure causes a higher velocity. We can also see this in the equation too. So if velocity increases, the pressure must decrease since this value is a constant, as we saw here. And this can explain how lift is created in airplane wings. So the design of the airfoil is designed so that more air particles go to the down the lower side of the airfoil than the upper side. So this will cause less particles on the upper side. This will cause the less particles on the upper side, which will create a lower pressure on the top, which will again cause the velocity of the air particles to become faster here, because of Bernoulli principle. And also, you can think of it this way. So there will be less air particles here. So then it creates sort of a vacuum effect, which sucks in the particles, which makes the air particles a lot faster than the lower part of the airfoil. Because of the difference in pressure between the upper side and the lower side, there is a net force of lift that goes up. Hence, airplanes generation of lift. So we will derive Bernoulli's principle, the equation of Bernoulli's principle without calculus in this session. So first we start with the network kinetic energy theorem. This states that the network, which is a transfer of energy by a force, so basically all the forces on a system, is equal to the change in kinetic energy of the system. If you've heard of the word system for the first time, system is just like a collection of objects or an object that, yeah, and this collection helps with the calculation of forces, and it also helps us define internal and external forces, which aid our calculations. Back to our equation. So this is the network, and if you know what net means, it means all the things added together. So so this is the work that is done from the fluid from the left side. And so just a reminder, this is this. So the pressure here does work on the fluid from the left side. And this is the same for the pressure that comes from the right side. So this is the work that comes from the left side, and this is the work that comes from the right side. And this is the work done by gravity. Since the fluid goes upwards, it travels a vertical distance, and for that vertical distance, gravity must do work because it has when the fluid goes up, the force of gravity puts work in. To better understand this concept, I will explain to you what work is more in detail. So we substitute this work 1 with this equation according to this. So F1 d1 cosine theta. And same for this. So this is the change in height. And same for this. So more about work. So work is basically the product of the horizontal component of the force. Sorry, excuse me. So it's basically the product of the force that is parallel to the object's movement. So as you can see, the object is moving parallel to the ground here. So we take the horizontal component of the force, which we can take by F cosine theta. So this theta is the angle that the force and the movement of the object is making. And we multiply that with the distance that the force was applied over. Hence, we get Fd cosine theta for work. Now, you can see that the F got replaced with P1A1 and that the cosines are all disappeared, but we can cancel out the cosines because the theta will be 0 degrees since the pressure, we're assuming that the pressure is exerted parallel to the movement of the fluid. And you might wonder why these are replaced with P1A1. And this is because pressure is equal to force over area, and this is the definition of pressure. If we do some algebraic multiplication, we get F equals PA, so we can substitute F1 with P1A1. Here, we have the force of gravity substituted by mg, and this is also the definition of gravitational force on an object. So this is the weight. And the delta y is substituted by y2 minus y1 since this is a change in height. And I just forgot to remove the cosine here. Never mind. Oh, so this cosine, so the theta here is different than these thetas. So the theta here, so the theta for these terms are 0, but the theta for this is 180 degrees, which is 180 degrees, which will be -1. So let me turn on the pen. So if the fluid is moving like this, the vertical distance will be like this, and the fluid will travel upwards. But the force of gravitation moves downwards. So the angle that is caused between these directions is, so theta would equal 180 degrees. So we substitute 180 degrees here, and then we get cosine 180 degrees is -1. So we change the sign here, and then we just use the distributive property to get these two terms. And for the change in kinetic energy, we use this formula. Kinetic energy is equal to half times mass times volume velocity squared. So this is the final velocity, and this is the initial velocity. And then we move all the 1 terms on the left side and the 2 terms on the right side. Then we substitute m with rho v. So this is called rho, spelled RHO, and is the density. So if you recall the definition of density, it's mass over volume. So it's how much mass is in a set space of volume. So if we if we manipulate this, we will get mass equals rho v. So we substitute the m's with the rho v here. So we do the same for pretty much everything. And then the next step will be v, to substitute v with a1 d1. So if you see this diagram, you'll recall that this gap times the cross-sectional area will equal to the volume of the cylinder. So that's why we substitute v1 into a1 d1, and then we do the same for all the others. And then we can cancel out the a1 d1s and a2 d2s because of what we said. So the area of this section will equal to the area of the section on the top, and never mind. The volume of the section from here and here will be the same. So a2 d2 represents the volume of the section on the top, and the a1 d1 represents the volume of the section on the bottom. And they must be the same since the fluid is incompressible and the fluid flow rate is the same throughout the flow tube. So we can cancel all these terms out, and then at last we get this final Bernoulli's equation. So the key takeaway of Bernoulli's equation is that if the velocity of the fluid becomes faster, the pressure becomes less. And if we put this in more physics terms, it would be pressure is inversely proportional to velocity. Next, we will talk about what experiment we will do to examine this Bernoulli's principle. So basically, we're going to use a hairdryer and 2 cans. So we will blow in wind in between those cans, and then the airflow between the cans will become faster, which will cause the pressure of the air between the cans to decrease, and this decreased pressure will be different from the pressure that's coming from the outside. So because of the difference between pressures, a net force will be caused between the cans, and then they will eventually collide when we do the hairdryer experiment. For more detailed procedures, we will post a link for this. Yeah, so now you have learned what Bernoulli's principle is. Now you can do the experiment. Thank you for watching.